So we're continuing on with 3.2 with discontinuities, and just a few reminders on how we phrase this. So what we first look for with the discontinuities is our restricted values. So as a reminder, that's setting the denominator equal to 0. Now we have two different kinds. We have removable versus non-removable. So removable is usually in the case where we have 0 over 0. And the phrase that we've used so far is a point discontinuity, which basically is a clue that we have a hole. I guess I could have written that right here. Is a hole in the graph. Might even be worth mentioning that the way that we phrased it before is as x approaches some a value on the left side, the function approach some b value, and as x approaches a on the right side, the function approaches the same b value on the right side. You may remember that from a previous unit. So here's a little picture of a removable discontinuity, and then the left end behavior. I said that wrong, but the left side and the right side approach the same value. So as we look at non-removable, sometimes it's of the form c divided by 0, where c does not equal 0. So if we have an infinite one, this might be a phrase for you. That is a clue that we have a vertical asymptote at on the graph, at that x value on the graph. So what would happen there is, let me use the same notation, as x goes to a on the left side, the function goes infinitely up or down. It doesn't actually matter, just pick one. And then same thing on the other one. As x approaches a on the right side, the function is going infinitely up or down. That's actually why we get that phrase infinite. But it is a vertical asymptote. So here's a picture. Again, this is a picture where they went to negative infinity and positive infinity on the left side. But you can flip those. They can be the same. You can still go in, both negative, both positive, and it would still be a vertical asymptote. And then the last one, I'm not too concerned with, so I'll just change colors because we're not looking at jump non-removable discontinuities. And basically, there's a lot of different ways that we could describe it, but, we could talk about as x approaches a on the left side and the function goes to c, and you just want to make sure that a on the right side is some different value. So I'm going to call it d. Maybe I should call this e because I've used c already, where e does not equal d. Something like that, which is exactly what's happening here. But I'm not going to stress too much about this because this is not part of a rational function. You're not going to see a jump discontinuity on a rational function. Now, as you look at this problem, these domains and ranges, just a nice friendly reminder on how to figure out the domain. Well, it's the x value, so it stops at 1, jumps over 1, basically, and goes infinitely to the right. And as you look at the range, it goes infinitely down. Yes, there's a hole at y equals 1, but it has a defined value at y equals 1, so it does go infinitely up. Every y value is defined. Now the domain and range on this one, it looks like the domain is still negative infinity to 1, jumps over 1, so put your union 1 to infinity. And then same thing is, just pick one arrow for your range, but they are going infinitely down and infinitely up. So negative infinity to infinity. And then this one, domain, actually this time, because it's a defined value right there, we can just say negative infinity to infinity. And then the range is still going infinitely down and infinitely up. So negative infinity to infinity. It doesn't have to be this way, but this is how these three graphs specifically were written. So that was good practice. So what we're doing is we're just adding to things, getting you to practice a little bit more. And we're going to practice, how we know some of these things. So how can we identify some of these items? So let's just practice for a second. So let's factor it. And by the way, the clues, because the graph is given to you, the clues in the graph might help you tremendously. For instance, if you identify that there's an x-intercept at -1/2, that might help you identify that your factored form would be like 2x plus 1. The fact that we have a hole at x equals 3, that might be a clue for you to say, okay, well, it has to be x minus 3. Now that only works if you are given the graph. If you're not given the graph, then you couldn't use that. And same thing with the denominator, is if it's a hole, it has to also be in the denominator, and then I'm looking at x equals -2 is the vertical asymptote. Vertical asymptote at x equals -2. So then x plus 2 needs to be a non-canceling term in the denominator. There's a hole right here. Hole is actually stated right there. Well, let's confirm that we factored that correctly then. So is 2x times x 2x squared? Yep. Outside is -6x plus 1x is -5x. And then 1 times -3 is -3. So that's correct. The numerator is correct. Factors in -6 that add to be -1. That would be x minus 3, x plus 2. So we factored correctly. So let's confirm a few more things. We cancel out the x minus 3. So that's your clue that x equals 3 has a hole. Now what's the y value? If you paid attention to the previous video, you plug in 3 into the simplified version. So if I plug in 3 here, 2 times 3 is 6 plus 1 is 7. Plug in 3 right here, 3 plus 2 is 5. So that confirmed that that hole was correct. We've already talked about the vertical asymptote is the non-canceling in the denominator. The non-canceling in the denominator. And then the non-canceling in the numerator is your x-intercept. So let's write that down. The x-intercept is -1/2, which is confirmed by right here. What are some other things that we can do? Is we can confirm the y-intercept. We haven't talked about that in a while. How do I know the y-intercept is 1/2? Well, plugging 0 in for all of these x's. 0 minus 0 minus 3, that would give me -3. 0 minus 0 minus 6, that's -6. That equals 1/2. Now the only downside to this is how would we know this portion of the graph? And a quick answer is that you can plug in any number to the left of -2 and see where it's at. And for our purposes right now, we're not going to cross the horizontal asymptote or the vertical asymptote. And I know I've not taught you the horizontal asymptote trick yet, but you will. We're getting there. We're slowly getting there. So let's just confirm everything we know. Just looking at g of x. So we're not quite there to graph on your own yet. That's my point. So if I asked you to factor, looking at x plus 1, x plus 3 will give me the numerator. Factor the denominator, that would be x minus 1, x plus 3. So as we look at the canceling term, x equals -3 is going to be your hole. Well, how do you figure out what the y-coordinate is of the hole? Go to your simplified. I haven't written it down yet. Go to the simplified and plug in x equals -3. Well, -3 plus 1 is -2, so just some scratch work. -3 minus 1 is -4. -2 divided by -4 gives me 1/2, so we can identify where the hole is. The other factor in the denominator is x equals 1. Since it did not cancel, is a vertical asymptote. What else do we know? Is the x-intercept at x equals -1. Why? The numerator equals 0. How do I know the y-intercept is -1? That's plugging in 0 for all these x's. See, I did that in red earlier. I'm tired of writing on my graph now. 0 plus 0 plus 3. 0 plus 0 minus 3. That equals -1. That's how you find your y-intercept. So we are slowly getting there. And just for the sake of practice, here's a few more. So h of x is not too bad. There's nothing to factor in the numerator. But you can factor the denominator. It's x plus 2, x plus 3. So don't let that fool you, because if you notice in this, because there's nothing left over in the numerator, there's still technically a times 1 there. But if I ask you for the x-intercept, let's start with that, is 1 can never equal 0. The numerator can never equal 0 in this problem. Because x plus 2 canceling out, that's your clue that you have a whole at -2. So it is okay to have no x-intercept. And there's actually another rule about the horizontal asymptotes, which we will get to. So how do we figure out what the y-coordinate is of the whole? Well, you plug in -2 into the simplified version. -2 plus 3 is 1. So 1 divided by 1 gives me 1. We have a whole right here. What else do we know? The non-canceling in the denominator. That's your vertical asymptote at x equals -3. What else do we know? The y-intercept. I almost had a brain fart of what we've learned so far. Is plugging in 0 here, so we're looking at 2 and 0 here over 6, so it equals 1/3, which I know that can be confusing. Some people think that was supposed to be 1/2. It was supposed to be 1/3 right there. So let's really hammer this home and just look at the last one, and then you should be ready for the homework. Again, I would encourage you to pause and try to factor on your own. Otherwise, you're going to see my very, very quick and lame answer of guessing and checking. 2x times x gives me 2x squared. I'm thinking about 2 times 2 is 4, and 3 to get me to 7. And 3 times 2 is 6. So that was correct. Now we have x plus 3, x plus 2, which is confirmed by everything that we've talked about so far. That the canceling is your whole. Whole is at -2. How do you figure out your y-intercept? We'll plug in -2 here and here. So we're looking at -4 plus 3 would be -1. And -1 plus 3, man, I did that wrong. -2, -4, sorry. -2 plus 3 is +1. +1. Anyway, you do get the right answer. The graph is right. I was wrong. There's a hole right there. Non-canceling in the denominator. Some students get this confused. They have to be exactly the same factors in order to cancel. So do not cancel out 2x plus 3 with x plus 3. That 2 ruins it. So vertical asymptote at x equals -3. Let's see, we have an x-intercept. It's the numerator. That would be x equals -3/2, or 1.5. Let me write it off to the side here. That's the non-canceling in the numerator. We can figure out the y-intercept by plugging in zeros for all these x's. So 0 plus 0 plus 6. 0 plus 0 plus 6. So the y-intercept is 1. I hope I don't have to explain, but I'll do it real quick, that 0 squared is 0 times 2 is still 0. 7 times 0 is still 0. 0 plus 6 is 6. That's how I can do the y-intercept really quickly. Some students just memorize it. You divide your constants, which is fine. I just like emphasizing that the y-intercept is when x is 0, versus the x-intercept is when the numerator equals 0. So make sure you distinguish between those, and I don't care how you do that. I'm just stuck in my ways, and you can do it your way. And you should be ready for the homework now.